Hello, and welcome to the third part in this series on the first worksheet of the summer again. So this one, it's called Java practice. I don't know why it's called that. It should be called recursion practice or something, because that's really what we're doing here. This is a problem where the actual Java syntax itself is probably pretty straightforward to you at this point, even if you're very new to Java. What's weird is the recursive thinking, and they do a really terrible job of trying to explain recursion in 61A if you've taken that class. So let's try to explain it in a way that actually makes some more sense. So here we have a method, and basically all it's doing is it's taking the individual digits of a number and summing them together. So we see the example here they give you is digits of pi summed together. So it just wants you to sum 3 and 1 and 4 and 1 and 5, and that comes out to be a number. What is it? It's 14 apparently. Okay. That makes sense, right? We're just trying to take every number and sum it together. But the hard part is we want to do it recursively. So the first thing I want to do here in terms of figuring out how to do this recursively is let's start with a smaller example, because 3 plus 1 plus 4 plus 1 plus 5 is all fine, but it's 5 things long, which is kind of long. Let's just do this example with 1, 2, 3. I think they'll be easier, right? It's pretty clear what this is. 1 plus 2 plus 3 is equal to 6. It's a perfect number. It's a triangle number too. So we're going to use the example 1, 2, 3 because it's easier, right? So not trying to write any code or anything. Let's figure out how we actually want to do this algorithmically, right? What do we actually want to do? So we want to somehow get every number in isolation and add them together. So I think naturally the first question that probably comes up is, do you want to go front to back or back to front? Do you want to add 1 plus 2 plus 3, or do you want to add 3 plus 2 plus 1? Give you a second to think about it if you would like. Shout out your answer now. But I think it's going to be easier to go 3 plus 2 plus 1. It's going to be easier to go back to front. Why is that? Because there's a very a kind of common trick you may have seen before that we do a lot in computer science when we want to get an individual digit, which is we just use like modulo basically. So notice if we just take 123, and modulo it by 10, we're going to get 3, right? Because we're going to basically get the remainder of that thing. That gives us 3. Once we have that, we no longer need the 3 in 1, 2, 3, right? Because now we have it as its own number. And so now we can divide 1, 2, 3 by 10. In Java, division rounds down. So 1, 2, 3 divided by 10, is going to be 12, right? Once we have 12, well, now we can modulo it by 10 again. That's going to give us 2, because 12 modulo 2. 12 modulo 10 is equal to 2. And then we can divide 12 by 10 again. Remember, we're rounding down. So 12 divided by 10 is going to give us 1. Then we can modulo 1. 1 modulo 10 is going to be 1. We can divide again by 10. 1 divided by 10 in Java is going to round down to be 0. Once we're at 0, we know at the end, right? This is a very common thing that I think is in like the first 61A homework too, so you may have seen it before. But basically, we have this process. We're going to modulo off the last digit. That's how we're going to get it. Then we're going to divide that number by 10. So then we can modulo off the next digit divided by 10 so we can get the next digit, right? That's the process we're going to do. And notice that that process, it doesn't necessarily imply anything recursive. It doesn't necessarily imply anything iterative. So if we come up with this general algorithm, we're going to be able to write it both ways pretty succinctly, both recursive and iterative, because this says you can do both. We're going to focus on the recursive one first. Okay, so let's remember, what is the process? The process is basically, we want to take our number, we want to modulo it, right? Get that number, then we want to divide by 10 to turn this 1, 2, 3 for in this example to 12, modulo it again. And how long do we want to go? We want to go until our number, which we're calling x here, is equal to 0, because once it equals 0, it's frivolous to keep doing this. We're just going to be adding zeros over and over again. So I basically turned it into these kind of 3 steps. These 2 steps are pretty much our algorithm: modulo, divide by 0, and then of course a little arithmetic to add things together. But that's really the root of the algorithm. And then this is not really a step in the algorithm; it's more just a stopping condition, right? And of course, with the recursive algorithm, we're going to want to have some kind of stopping condition. So now we can actually start to build the recursive algorithm, right? What's our stopping condition? What is our base case, as the term usually goes? Well, the base case is just going to be when x is equal to 0, or I'm just going to say less than or equal to 0 just for fun. That's what the official solution says, but you could just say equal to 0 because you're never going to divide something and get a negative number here when you're starting with a positive number. But basically when it's less than 0. Okay, now normally in a base case, we want to return something. What do we want to return? Well, let's consider what we would return in this base case. So if x is equal to 0, what is the sum of all of x's digits? It's just 0, right? So this is our base case, right? Trivial. So now we have to do the actual recursive part. That's where we have to kind of figure out how to add these things together. So this is probably the hard part if you're doing a recursive function, but instead of trying to do it all in one go, let's kind of think, what are the elements of a recursive function? Well, by definition, a recursive function is one that calls itself. So we know somewhere here, we're going to be calling some digits, right? Otherwise, it wouldn't be a recursive function. We know that's going to be in there somewhere. We also know we have to do this module, we have to do this divide every time. So when are we going to do it? Well, the first thing we want to do is, if we have the number 1, 2, 3, we want to modulo by 10 so we can get the 3. So let's just do that. 1, 2, 3 in this case is x. So we're just going to do x modulo 10, right? And we're going to add that to something. I hope so far this makes sense. You can do this in multiple lines too, but I'm just going to do it all in one. What are we going to want to add it to? Well, this is where the recursive part comes in. We know we need to have a recursive part somewhere, and we want to add 3 to 2, right? And 2 is something we're going to get recursively. So this is where we're going to do some digits, and we're going to add to that. So remember, we need one more thing. We need to divide by 10, and it makes a lot of sense to do it here. So we're going to do x divided by 10 because that's where some digit is going to come into play. Okay, I know I did that all pretty quickly, but hopefully you can, if this seems like it's a lot to do, remember that really this whole thing here, this last line, is consisting of 3 steps. We know we need a modulo at some point. We know we need to divide by 10 at some point, and we know we need to include some digits at some point. Otherwise, it wouldn't be recursive. From there, it's a matter of taking those 3 components and fitting them together. And hopefully this makes a little bit of sense, because for any given x, first thing, for any given x, whether it be 1 or 12 or 1, 2, 3, we want to modulo off the last digit. So that's where this comes from. And we want to add that to all the other digits, which is going to be done recursively. Now, if we were in 61A right now, I would just tell you, oh, trust the recursion and do the recursive leap of faith, and then you can, know that it works. Here's a secret about the recursive leap of faith, is that it's complete bullshit. The recursive leap of faith is super stupid. I hate that they teach it. All it does is it encourages you to write code that you don't understand yourself. So here, instead of doing the recursive leap of faith, we're actually going to look at this function and we're going to try to understand what it's doing recursively. Writing it is one thing, but the more important thing I want you to understand is why this actually works. I'm going to use the example 1, 2, 3 again, just because it's a lot shorter than 3, 1, 4, 1, 5, but you can imagine how this would generalize. Okay. So let's say that we call some digits on 1, 2, 3. What's going to happen in the computer? What's it actually going to do? It's going to do something recursive, but let's look through. So I'm going to introduce the concept of frames here. If you took 61A, you're probably familiar with frames. A frame is just a given execution context for a function. So to start, we're going to be in the kind of global frame, which I'm going to call F0, right? That's the frame we're in when we are calling this function for the first time. So let's say we call some digits on 1, 2, 3, on 123. Well, in the first frame, we're going to have a variable called x, which just comes from here. And it's going to have a value 1, 2, 3, because that's what we gave it, right? So let's go through the function and see what's actually going to happen. So the first thing it's going to do is it's going to say, is x 1, 2, 3 less than 0? It's not, so we're not going to take this if condition. So we're going to go into this returns line. So we're going to want to return something. So we're going to return x modulo 10. 123 modulo 10 is just 3. So it's going to return 3 plus some digits. This is where the recursive part comes in, because the computer is going to say, oh, you want to return 3 plus, something. But in order to get that something, you have to execute this function before you can do it, right? If this wasn't a recursive function, this could be any other function, right? You would have to evaluate it before you can add it to 3. So what it's going to do is it's going to create another frame, which I'm going to call F1 here. And it's going to execute that. And then once it's done executing that frame, it's going to return up to F0. So what's F1? Well, F1 is another call to some digits. So it's going to have a variable x. And what is that variable x going to be in this frame? Well, here we say sum digits is going to take x divided by 10. 123 divided by 10, rounded down because we're in Java, is going to be 12. So in this frame, we have x is equal to 12. Right? So now we go ahead and we start executing this frame. Remember, this frame up here still exists. We're just waiting on this thing. It's just kind of putting on a hold. It's saying 3 plus something. What is something? Well, it's whatever this frame down here is going to return. So now we basically started back up at the top of the function again. We have an x that is now equal to 12. So it's going to say, okay, if x is less than or equal to 0, it's not because it's 12. So we're going to go onto the return line. Same thing's going to happen as before now. We're going to return something. We're going to return 12 modulo 10, which is just going to be equal to 2, right? Plus something else. Oh no, what is that something else? It's another call to sum digits. So we're going to do the same exact thing we did before. We're going to create a new frame, which I'm going to call F2. And we're going to evaluate that frame. Once we're done evaluating that frame, it's going to return up to here. Okay, so what is x in F2? Well, we took 12 now and divided it by 10, so x is just going to be 1, right? And then same thing is going to happen. It's going to say, okay, is x less than 0? No, 1 is not less than 0. It's going to skip over that, and it's going to return 1 modulo 10. 1 modulo 10 is just 1, plus something. What is it? It's another call to sum digits, and this is going to be our last call to sum digits. So we're going to do F3. I promise it'll be the last one. And now what is x in F3? It is finally 0 because remember in F1, we just took 1 and divided by 10. What is 1 divided by 10? It's 0 in Java. It's really funny because in Java, you get these really weird statements where you're like, oh, what's 5 divided by 2? It's 2. You just get used to thinking that way. But anyways, so now we're going to start executing this frame. We're going to say is x less than or equal to 0? Well, x is now 0, so it actually is, right? So we're going to go into this line here finally and return 0. We're going to return 0 finally. We're not going to go another frame deeper. We're never going to run this line because we hit this 0 first. Okay, we're going to return 0, but where do we return it to? Well, we're a number of frames deep, so we're going to return it to this frame, right? Right here. That was supposed to be a circle, but it actually looks a lot like a 0, right? So we're going to return the 0 up to the frame that we were waiting on, because remember, we have all these numbers waiting. 3 is waiting for the result of this frame. 2 is waiting for the result of this frame. 1 was waiting for the result of this frame. Now we have the result of F3. So we're just going to add it. So now we're going to return from frame 2, 1 plus 0. 1 plus 0 is just going to be equal to 1. Where are we going to return that? Well, 2 is waiting on the result of, or sorry, F1 is waiting on the result of F2. The result of F2 is now 1. So now we're going to say, okay, return 2 plus 1. 2 plus 1 is just 3. That is going to return up into this next frame into F0. That's going to be 3. So now we're going to get 3 plus 3. Return 3 plus 3. This is 6. Where are we going to return this to? We're going to return to the user because now we're finally in frame 0. That's how everything works, basically, recursively. We're just going to calculate the result. We're just going to go down to the deepest frame, calculate a trivial result in the deepest frame, right? We're just going to say 0, and then pass that up successively to frames so that we can continue our calculation all the way back up to the top. This might be very confusing. If it is, I'd recommend you watch the video maybe another time because I really did a bang up job just explaining it now. But this is how recursion actually works in your computer. There's no leap of faith here, right? You can just prove it to yourself on a small example. The real leap of faith is assuming, okay, well now I've just proven it to myself on an example of size 3. Would it work on an example of size 6 or something, or size 10? And it would, right? You can see how this process would generalize. Anyways, that's how you do the recursive version of this. I will also do the bonus, the iterative version. And a thing to note about the iterative version is remember the process we developed. We take our number x, we modulo off the last digit, then we add that, and then we divide, we modulo off the last digit, and then we divide our number x by 10 and do the same thing, right, over and over again. That algorithm that we came up with at the very beginning, it's not recursive, it's not iterative, it's either, which means we can apply it to both iterative and recursive functions. So let's do it iteratively now. So if we're doing something iteratively, we're probably going to want to have like a variable called total, which we're going to start at 0. And then we're going to want to go through the digit. the digits. I'm going to do this with a for loop, right? Because remember, we have an iterative process here. We want to take 1, 2, 3, for example, divide it or modulo out the 10, divide it by 10, modulo divide over and over again. You could do this with a while loop. I really recommend you do it with a for loop as you go on in computer science. You're probably used to using while loops a lot from like 621A, but for loops are much, much more common. They're much more useful. They're much more powerful. And although it may not seem this way right now, they're much easier to read than while loops. So I encourage you to do it with a while loop rather than a for loop. Or sorry, with a for loop rather than a while loop, the other way around. Right now, I'm just going to write out the for loop. I don't really know what's in it yet. So now we want to think of our process. Well, we want to start with x. Let's say that x equals 1, 2, 3. We want to basically modulo this number and divide, modulo, divide, modulo, divide. So there are 3 parts to a for loop. The first part is instantiating a variable, and it sounds like we want to instantiate, I'm going to call it n, just as whatever x is, right? Because we want to start with 1, 2, 3, modulo something out, then divide, right? So let's start it like that. And then we also know our base case. It's the same thing as the recursive base case, right? Once we want to execute this loop so long as our number, which is n, is greater than 0. This is kind of the opposite of what this one is, but it's the same idea, right? Because this one is just saying once our number gets small enough, basically stop execution of a recursive function, right? Go back up the recursive stack. This one is saying once our number, or sorry, this is supposed to be, I drew that the wrong way. This is supposed to be n greater than 0. This one is just saying so long as our number is greater than 0, continue execution, right? So this one is describing, you know, they're both describing when we stop. It's just kind of the opposite. It's just kind of opposite ways of doing it. Okay, and I'm not going to worry about the third condition right now. We'll talk about that in a second. So this is kind of the like setup. And now what we want to do is we want to add the total every time, right? So total is going to be itself plus something. What is it going to be plus? Well, remember, all we're doing is we're just going to modulo off the last digit. So we're going to take n, modulo off 10, and that's perfect, right? The next thing we're going to do is every time we modulo the digit off, we then want to divide our number by 10. So I'm just going to do that up here. I'm going to say n is going to be equal to itself divided by 10. This kind of looks like a 1. It's supposed to be a division symbol, sorry. This shorthand of like slash equals, it just means itself divided by 10 in the same way that n plus equals, you know, means itself plus something. But if you want, you could also write this out manually down here. You could write, you know, n equals itself divided by 10 and just not have a condition here, something like that. There are a lot of ways to write this loop, but this is doing the exact same thing the recursive one is doing, and it's doing the exact same thing our algorithm is doing, right? It's starting out with 0, and then it's basically just saying, okay, we want to start our value at x, which is going to be 1, 2, 3 in this basic example. We want to modulo off the last digit, then go through and divide by 10, modulo divide. How long do we do that? Well, we do that so long as we have something to divide and modulo, which is what this n greater than 0 means. That's basically the loop, and that's basically the function. Last thing to do is remember you actually need to return something. Pretend this bracket isn't here. You want to return total. Don't worry about that. You want to return total after we've calculated everything, otherwise it won't compile, right? Because you need to return an int is basically what it's saying. So that's how you do it iteratively. I hope you see that it's really, really similar to the recursive one. It's basically the same thing in reality. But yes, that is the third part of this video.